Modern enterprise networks are undergoing a change in population. Alongside human developers, thousands of autonomous agents are actively pulling repositories, scanning databases, and deploying infrastructure. This machine activity is quickly becoming the dominant force in the pipeline. Across the development lifecycle, non-human to human identities now sit at an 82-to-1 ratio. The immediate reaction for many engineering teams is to rely on their existing CI/CD pipelines to absorb and secure this new digital workforce. Traditional security architecture relies heavily on stage gates, static checkpoints placed at specific intervals in the development process to review and authorize work before it moves forward. In the context of a software pipeline, these stage gates usually take two specific forms: merge request approvals requiring a peer review, and protected branch rules that block unauthorized code merges. These controls are calibrated for human speed. That is, soon a developer spends hours writing a feature, followed by an explicit pause to ask for a code review. When you apply security checkpoints designed for human workflows to actors moving at machine speed, the control mechanism fails to catch threats in real time. To understand exactly how this failure occurs, we have to look at the operational mechanics of an autonomous agent completing a task inside a repository. Agents operate by chaining together a sequence of privileged tool calls. They might read a file, execute a script, and query a database, feeding the output of one step directly into the next. A human might perform these actions sequentially over an afternoon. An agent executes the entire chain in milliseconds. This diagram illustrates the problem. In the standalone security model, a protected branch rule evaluates changes only after the agent has chained multiple tool calls. Merge requests gate the final merge, but not the upstream actions taken to prepare it. This creates a severe exposure window. By the time an AR is flagged for human review, the agent has already accessed infrastructure, read files, and potentially moved sensitive data. Securing automated workflows requires a change in approach. It demands moving away from reactive stage gates in favor of a runtime authorization plane that intercepts every individual machine decision in under 10 milliseconds. Let's trace a standard automated task to see how runtime interception works. Suppose you invoke an agent to refactor a billing service. This timeline maps the agent decision flow. The system intercepts the agent's very first tool call. Every request routes through a policy decision point, or PDP. Backed by Open Policy Agent and Rego, it evaluates the call's parameters against your defined security rules. In this case, the engine verifies that reading the billing repository is within scope for this specific task, and it instantly permits the action. Because the network request is intercepted and evaluated before execution occurs, security becomes a proactive shield against unauthorized actions, rather than a post-incident report. Now watch what happens when the agent makes an error. It hallucinates a requirement for live testing data and attempts to query a production database containing personally identifiable information. Moving forward to step 3 on the timeline, the agent attempts the tool call targeting the production database. The PDP evaluates the request, and the action is immediately denied at runtime. The system achieves this by using an attribute and relationship-based access control engine, feeding live context into the evaluation rather than relying on static permissions. The context engine recognizes a mismatch. The data class of the target, production PII, is too sensitive for the agent's current task parameters, overriding any broad developer privileges the agent might have inherited. The agent corrects course and finishes the refactor safely. It then initiates the final phase, attempting to open a merge request to the main branch. At step 5, the PDP evaluates the request to merge. But here, the authorization adapts. Instead of a simple allow or deny, the engine flags a step up required alert. Because merging code into the main branch carries a high risk threshold, the PDP enforces a human in the loop requirement, pausing the agent's progress until a human verifies the logic. This context-aware, per-action routing stops unauthorized data access the exact millisecond it is attempted, without throttling the velocity of legitimate development tasks. Blocking an unauthorized request is the operational baseline. Proving to auditors that you maintain total control over your AI workforce is the enterprise necessity. Every single evaluation the PDP performs, every allow, deny, and step-up decision generated in under 10 milliseconds is captured in an immutable decision log. This translates opaque AI behaviors into exact records of who requested what and exactly why it was permitted. It generates continuous compliance evidence for regulatory frameworks like SOC 2, PCI, or the EU AI Act. This continuous telemetry stands in contrast to legacy compliance models, which rely on point-in-time snapshot audits that tell you what happened long after data has left the building. An active, immutable audit log strips agents of their default overprivilege, verifying and logging every command to enforce a true zero-trust posture per action. Despite the need for mathematical certainty, many engineering teams attempt to secure their agents simply by writing restrictive system prompts, telling the AI not to access sensitive data. There is a structural difference between a natural language prompt and a hard-coded security policy. A prompt can be bypassed by an anomalous hallucination or a jailbreak. A policy as code rule is an unyielding barrier. Policy as code provides the only mathematically rigid, deterministic control available to enterprise security architects. Natural language requests to an LLM are merely suggestions. Politeness is a prompt layer. Security is a policy layer. Securing the agentic software development lifecycle requires an uncompromising sub-millisecond policy layer, acting as the final arbiter of every machine action.